Part 1, Chapter 1, Circular Motion. In daily life, we come across various practical situations where motion is involved. See here, the cyclist is traveling along a straight road and he is performing a rectilinear, or we can say a linear motion. But when he takes a turn along a curved road, what he performs? A curvilinear motion. And when he moves along a circular racecourse track, what he performs? He performs a circular motion. So in circular motion, the particle revolves along circumference of a circle. The common example, motion of Earth and other planets around the Sun. Then angular displacement. Here we can see a particle performing uniform circular motion along the circumference of a circle with center O and radius R. It is moving in anti-clockwise sense. A vector drawn from the center of the circle to the position of the particle is radius vector. If we consider the center O of the circle as the origin of the frame of reference, the radius vector also serves as the position vector. Now the radius vector goes on changing its direction as the particle moves along the circle. Consider the particle performing circular motion in anti-clockwise direction. Let A be the initial position of the particle when t is equal to 0 on y axis. Let B be the position of particle performing circular motion after time t. The angle theta gives position of particle at instant t, and the angle theta is called angular displacement of particle in time t. The angle subtended by an arc AP at the center O of circle is angular displacement. So, angular displacement is defined as the angle described by radius vector in a given time at the center of circle. If a particle performing circular motion completes one revolution, then angular displacement is equal to theta is equal to 360 degrees is equal to 2 pi radian. Now 1 radian is the angle subtended by an arc of the length equal to radius of the circle. So theta in radian is equal to arc length divided by radius. So theta is equal to S upon R. So S is equal to R theta, say equation 1. When the particle performing circular motion moves from A to B in very short time interval delta t, then it describes the arc length delta S. So the angle traced by radius vector at the center of the circle is delta theta. So in this case, delta theta is equal to delta S upon R, say equation 2. Instantaneous angular displacement is a vector quantity. Therefore, delta S vector is equal to delta theta vector cross R vector, equation 3. The direction of angular displacement is given by right hand rule or right-handed screw rule. So what is right hand rule? Imagine the axis of rotation to be held in right hand with the fingers curled around it and thumb outstretched. If the curled fingers give the direction of motion of a particle performing circular motion, then the direction of outstretched thumb gives the direction of angular displacement vector. Next is angular velocity and angular acceleration. Angular velocity. The rate of change of angular displacement with time is called angular velocity omega of the particle. Consider a particle performing a circular motion along a circle of radius r in anti-clockwise sense. Let theta and theta plus delta theta be the angular displacement of particle in time t and t plus delta t respectively. Thus, delta theta is the angular displacement of particle in time delta t. Instantaneous angular velocity omega bar is equal to limit delta t tends to 0 delta theta bar upon delta t. So omega bar is equal to delta theta bar upon dt. equation 1. Also, finite angular velocity omega is equal to theta upon t. The SI unit of angular velocity is rad per s and the dimensions are L0, M0, t minus 1. Angular velocity is a vector quantity. The direction of angular velocity is given by right hand rule and it is in the direction of angular displacement. Then angular acceleration alpha bar. Whenever a rotating body speeds up or slows down, the angular velocity changes, and hence rotating body is said to possess an angular acceleration. Let omega 0 and omega be angular velocity of a particle performing circular motion at instant t0 and t respectively. Angular acceleration is defined as the rate of change of angular velocity. Average angular acceleration is equal to change in angular velocity upon time. So alpha bar is equal to omega bar minus omega 0 bar upon t minus t0. So alpha bar is equal to delta omega bar upon delta t. Instantaneous angular acceleration is the limiting rate of change of angular velocity. So alpha bar is equal to limit delta t tends to 0, delta omega bar upon delta t is equal to d omega bar upon dt. The SI unit of angular acceleration is radian per s square and the dimensions are L0, M0, t minus 2. The direction of angular acceleration is same as that of angular velocity if omega bar is increasing and it is opposite to that of omega bar if omega bar is decreasing. It is represented in magnitude and direction by using right hand rule. For example, when an electric fan is switched on, the blades of fan move with increasing angular velocity with time. So the angular acceleration will have same direction as the angular velocity. When the electric fan is switched off, the angular velocity of the blade of fan decreases with time. So the angular acceleration will have direction opposite to that of angular velocity.